Today, we're going to look at an old problem back from Calculus 1. We're going to look at a function, find the critical points, and then classify the critical points as a local minimum, a local maximum, or neither of those. So it's going to be a two-step process that could involve two of our derivatives. First, we're going to find the critical points by solving the equation f prime of x equals 0. We're looking for points where the function is flat. And that means there's a horizontal tangent line. That means the slope of the tangent line is 0. That means the derivative is equal to 0. Then we want to classify each of those critical points as a local minimum, a local maximum, or neither. We had a few options for doing this. We could use the first derivative test. That is, check for a change in direction. Look for a maximum by finding where the function goes from increasing to decreasing, or a local minimum where the function goes from decreasing to increasing. We could also check using the second derivative test, where we just check the concavity at the point. This requires that we take another derivative, but then we just have to plug in 1 point. So with the first derivative test, we have to plug in 2 points, one on either side of the critical point. Or the second derivative test, where we have to take a second derivative, but then we just have to plug in 1 point. We can also just look at a graph of the function, but we're trying to learn something here and see how this connects to other stuff. So we're going to do this the hard way. So let's solve the equation f prime of x equals 0. We'll take the derivative, 3x squared plus 6x minus 9, and we'll set this equal to 0. Now, on take 2, I have a polynomial that is factorable and that I can easily factor. I don't know about y'all, but I can easily factor at 8:30 on a Monday. So I'm going to take out the 3, and that leaves an x squared plus 6x plus 2x. Oh, maybe I can't factor this easily. X squared plus 2x minus 3. And then the x squared plus 2x minus 3 is an x plus 1 and an x minus 3. We don't care about the 3. We care about the zeros. So there's a 0 at -1 and +3. So the critical points So we have critical points at x equals -1 and x equals +3. Now that we see that there are 2 critical points in this cubic function, if we know stuff about polynomials, we know that this function looks like, and so we can read the leading coefficient. We know what the function looks like. We know that this function goes up, down, and then up again. It's a cubic, so the ends have to go in opposite directions. It has a positive leading coefficient, so it rises to the right. So it must make, if there are 2 critical points, it has to make 2 turns. So it looks like we're going to have to have a local maximum at -1 and a local minimum at 3. Knowing more is always better. This doesn't mean that we're going to stop the problem now, because finding the critical points and classifying them is not the point of the problem. The point of the problem is to take what we already know and see how that the calculus fits this description. We want to make sure that the calculus that we do fits this description. So I'm going to employ the second derivative test to check for concavity. If I know that if I plug -1 into the second derivative, what we know about polynomials tells us that the second derivative should be negative, indicating that the function is concave down at -1, indicating that we should have a local maximum at -1. So let's use the second derivative test on each of these critical points. So we'll take the second derivative, f double prime at x is going to be 6x plus 6. And we'll just evaluate the second derivative at each of the critical points. So f double prime at -1 is 6 negative 1s plus 6. Why am I getting 0 for the second derivative? What did I do? I should not be getting 0 at for the second derivative at -1. All right. What did I do? What am I not seeing? Oh,
The factoring part. Yeah.
awesome. Algebra got me. It should be x plus 1, minus 1, and x plus 3. Thank you. So we have x equals +1 and x equals -3 for our critical points.
And it's going to be x plus 3. You put negative.
Put negative. X plus 3. So it should be at -3. So -3 is where we're going to have our maximum, and +1 is where we're going to have our minimum. Do I have this right now? So plus 3x plus x plus 3 is the factor. X equals -3. All right. Now we're plugging in 1. I don't know if that was a more coffee problem or a less coffee problem, but I'm pretty sure it was a build problems backwards. And I wanted these to be my critical points. And then in my head, I'm just like, all right, it'll be this. And then I just grab those. Classic algebra mistake. All right, so where were we? Now that we have the correct critical points, we got x equals +1 and x equals -3. When I plug 1 into the second derivative, I get 12, and 12 is positive. So the second derivative is positive at 1. So that tells us that f is concave up at 1. And if we have a function that is concave up at a critical point, that means the critical point is going to be a local minimum. Now let's check -3. And we know what the result is going to be. We get -18 plus 6 is -12. So the second derivative is negative at -3. So that means f is concave down at x equals -3. And so f has a local maximum, concave down is a max, at x equals -3. Any questions? I guess inadvertently we illustrate the point of that knowing more is better. I knew what was supposed to happen. And so when I was getting 0 for my second derivative, I knew that there was not an inflection point at the critical point that I was worried about. I knew that that should have come out to be strictly positive or strictly negative because of the function that I thought I had built, or the function that I definitely did build, but didn't analyze correctly. So at least I knew there was something wrong. Now, if I could just stop making sign errors, which is impossible. You never stop making sign errors. They stay with you forever. Ask me how I know. So the overall picture is we wanted to find and classify critical points. We find the critical points by setting the first derivative equal to 0 and solving. Then we classify the critical points by looking at the second derivative. Any questions? All right. Now, as promised, we need to upgrade this same problem for a function of 2 variables and see what additional things we're going to have to be concerned with. Suppose that f of xy is x squared minus 2x plus y squared minus 4y plus 5. Let's suppose that we want to find the critical points and classify each as a local max, a local min, or neither. So it's the same question. Find critical points. And classify each as a local max, min, or neither. It's the same question. We're just starting with a function of 2 variables. Find the critical points is set the first derivative equal to 0 and solve. And then classify as a matter of checking in the second derivative. Let's see how that would look in this function of 2 variables. So the first step, we want to find the critical points. We want to solve f prime of x equals 0. But we have to do this for a function of 2 variables. So we don't have an f prime of x. We've got 2 derivatives. We've got fx of xy. So the derivative with respect to x is 2x minus 2. And we'll have a derivative with respect to y of xy, which will be 2y minus 4. So we don't have one derivative that we set equal to 0 and solve. We end up with 2 derivatives. So we're looking for points where the function is flat in both directions, flat in the x direction and flat in the y direction. So what we end up with is a system of two equations and possibly two unknowns. I took it easy on myself and gave myself essentially just a combination of two single variable functions. This is because lazy. But what we're trying to do now is solve fx equals 0 and fy equals 0. We're looking at a system of two equations. So upgrading f prime x equals 0, we're going to upgrade this to solve the system fx equals 0 and fy equals 0. Two equations and up to two and possibly two unknowns. Here we have a real easy system to solve. The first equation tells us that x is equal to 1, and the second equation tells us that y is equal to 2. So it looks like we have but one critical point. F of xy has one critical point. One, two. Some of you was looking at this function and saying, Leach, I'm not fooled by your minus 2x or your minus 4y. I see a circular paraboloid. And so of course we're going to have one critical point. There's a circular paraboloid and it's opening upward. So it's going to have a lowest point, and that lowest point will be at 1, 2. So the algebra tells us what we should find. Assuming, of course, that I factored things correctly. Fortunately, I don't have to. So the algebra is telling us that this is what we should find. The algebra is also telling us that this is going to be a local minimum, and it's going to be a global minimum because of what the function looks like. So the function is a circular paraboloid. But instead of the lowest point being at 0, 0, the lowest point will be at 1, 2 on the xy plane. This is because the x squared minus 2x, if we complete the square on x squared minus 2x, I need a plus 1. And if I complete the square on the y squared part, I need a plus 4. And that leaves plus 0. So moreover, this point is sitting on the xy plane. So we have a circular paraboloid where the center of the circles are going to be at 1, 2. If we have more values of x and only one value of y, then we just make combinations of the two. The purple 4 came from completing the square. Half of 4 squared is 2. Half of 4 is 2. 2 squared is 4. So y squared minus 4y plus 4. This plus 4 completes the square of the y minus 2 squared. And there was a plus 5, and the plus 5 is distributed with the plus 1 and the plus 4. If this had said plus 6, then I'd still have a plus 1 out here instead of a 0. And this whole paraboloid would be moved up 1 unit. But right now, the vertex is sitting on the xy plane, because after completing the square, we have plus 0 for a constant. Once again, the other reason that I picked this is that I wanted to make sure that our algebraic intuition, what we know about the graph, matches with what the calculus is telling us. This is why we start with problems that we should recognize. This is also why I say it's a lot to remember, and you have to remember all of it all the time in perfect detail. You have to think all the way back to the beginning when we started talking about surfaces. A function of two variables will produce a surface in R3, and we should be familiar with some common surfaces. Just like back in the previous problem, we started with a polynomial. And so if we know more stuff about cubic polynomials, then we know what we should be getting. Here's the tricky parts. Next, I wanted to check the second derivative, but now we're running into a new problem. So here's the part where we would be checking in the second derivative. We would take that 0.12 and we would want to check it in the second derivative. But the problem is we have two derivatives. We've got fx at xy, which was 2x minus 2. And we had fy at xy, which is 2x minus 4. So the problem is we don't have a second derivative. We've got 4 second derivatives. So that's our new problem. Now we have 4 second derivatives. We don't just have a second derivative, we've got 4 of them. Because I could take the derivative of fx with respect to x and the derivative of fx with respect to y. So here's some new notation for us. So each of our 2 partial derivatives will have 2 second partial derivatives. So I could take the derivative of fx with respect to x, and that'll just be a 2. I can also take the derivative of fx with respect to y, and that'll give us 0. Fy also has 2 partial derivatives. The derivative of fy with respect to x at xy will be 0, because there's no x. This should say y. And the derivative of fy with respect to y at xy will be 2. So there are our 4 partial derivatives. Previously, what we wanted was to look at the second derivative and determine if at a critical point if the second derivative is positive or negative. But there are 4 things running around here. What do I do with these 4 functions to just decide positive or negative? So we're going to have to figure out something, some way of combining these 4 functions to determine positive or negative. So we could say, I guess, the multivariable version of concave up and concave down. On one hand, this one worked out pretty simply and it fits our intuition. In the x direction, we see we must have a minimum because we're looking at concave up. And in the y direction, we're looking at concave up. But what are these mixed partial derivatives going to tell us? So how are we going to combine these 4 derivatives, these 4 second derivatives, to classify critical points? how are we going to use all 4 of these second partials to classify the critical points? So right now we're thinking it's a good thing that we know we have a local minimum at 1, 2 for this function based on the geometry and based on what we know about the surfaces and based on what we know about how polynomials work and completing the square works and how to find the center of a circle. But then again, that's a little less comforting when we remind ourselves of the fact that classifying this critical point was not the point of the problem. Coming to these 4 second partial derivatives and asking the question, well, shoot, what are we going to do now? How are we going to make this fit with our intuition about the problem? Any questions? So this has brought up the second order partial derivative question. If we have a function of 2 variables, we'll have 2 first partial derivatives and then 4 second partial derivatives. So now if we have a function of, when we had a, well, let's think back. When we had a function of 1 variable, y equals f of x, life was simple. We had a first derivative, and we could just say f prime of x, and then a second derivative, f double prime of x. Back when life was easy in Calc 1, there was only 1 variable to work with, unless we were trying to build a function, then we only got 1 variable to work with. But we ignored that part. And we're like, oh, yay, product rule, quotient rule, chain rule, again. But now we've got a function of 2 variables. So we're going to get 2 derivatives, fx at xy and fy at xy. And each of these derivatives has 2 partial derivatives. fxx at xy and fxy at xy. fyx at xy and fyy at xy. We can see how this can only expand from here. If I have a function of 3 variables, then I'll have 3 first partials, and each first partial will have 3 second partials. So we'll have 3 first partials and 9 second partials. I don't want to write that down because then I'd have fxxx as one of them. And, you know, we should at least try to stay PG-13. So like 2x. But at least when we get to second partials of a function of 2 variables, we have the student derivative, fyy, because that's what students are always on about. Why? So this is just a skill. So once I say there are second derivatives, you say, oh man, I should have checked the table of contents and seen what section is going to have second order partial derivatives. And in this case, it happens after the chain rule. So if we have a function of 2 variables, let's say xy squared plus 3x squared e to the y. Let's find the 4 second-order partial derivatives of this function. And let's see if it will fit in this space. Oh, also in the last 4 minutes. All right, that's right, I lost time because I had messed up that first problem. And then I confused myself by factoring it wrong. So let's find the first partials, fx at xy, because this is good practice. So I have x times y squared. Here, the y squared is just a constant factor with the x, so the derivative of x to the first is 1x to the 0, so we just get the constant y squared. Over in this second term, I'm taking the derivative of 3x squared. E to the y is a constant factor, so it just tags along. The derivative of 3x squared is 6x, and e to the y is a constant factor. Now, if I want to go on from here, if I want to find fxx at xy, I start with fx and take the derivative with respect to x. Y squared is now a constant term, so the derivative of y squared is equal to 0. E to the y is a constant factor, so I'm taking the derivative of 6x, and then I'll just multiply by e to the y. So the derivative of the y squared is equal to 0. We wouldn't normally write that, but I want to make sure that we see where it comes from, or what happened to the y squared. The derivative of 6x is 6. E to the y is a constant factor. I also have to look at fxy. So look at the function, or look at the first derivative fx, and take the derivative with respect to y. So fxy at xy. The derivative of y squared is 2y. Y is the variable now. 6x is now a constant factor. So I take the derivative of e to the y. Derivative of e to the y is e to the y. 6x is a constant factor. So there's our fxy. We also need to go back and get the other first partial derivative, fy at xy. So now I'm looking at y as the variable. So I'm going to take the derivative of y squared, and x is a constant factor because we're taking the derivative with respect to y. The derivative of y squared is 2y. So x is a constant factor. I just have 2xy. The derivative of the second term with respect to y, e to the y is the function. 3x squared is a constant, so we just get plus 3x squared, constant factor, times the derivative of e to the y, which is e to the y. So there's fy at xy. Now I need the 2 second partial derivatives, and that just means find the x and y derivatives of fy. I'll start with fyx at xy. Now I'm going to look at this fy, but now x is the variable. So in this first term, I want to take the derivative of 2xy, but y is the constant factor now, because we're taking the derivative with respect to x. The derivative of 2x is just 2, so I end up with 2. Y is a constant factor. In the second term, I want to take the derivative of the 3x squared, because e to the y is a constant factor. The derivative of 3x squared is 6x. E to the y is a constant factor. At this point, you might start getting suspicious. My fxy was equal to my fyx. Is this a coincidence, or will this always happen? Always is a tricky word to use in math, but yeah, that will always happen. Unless I do something specifically to disrupt this. So you can kind of count on that. Kind of count on that. Well, let's find our fourth second partial. Now I'm going to take the derivative of 2xy plus 3x squared e to the y with respect to y again. So y is once again the variable. X is a constant factor. The derivative of y with respect to y is 1. So I just get the constant factor 2x. 3x squared is a constant factor. E to the y is the function. The derivative of e to the y is e to the y. So I have 2x plus 3x squared, constant factor with respect to y, times e to the y, the derivative with respect to y. So here are our 4 second partial derivatives. All we have to do now is thousands of problems where we find the 2 first partials and the 4 second partial derivatives. And we'll be really good at this skill. Then we'll finish calculus class and graduate, and then we'll never have to find second partial derivatives by hand again.
I have a question.
Yes.
Is it always the 2 middle, it's going to be the same?
Not always. The function has to have continuous second partial derivatives. So we can build a function where these two are not the same, but in most situations, they are going to be the same. So
Okay,
almost
thank
always
you.
the same. I guess a good way to go about it is to find fxy, or whichever one seems easiest, and then just assume fyx will be the same. And if something breaks in your problem, go back and check to see if fyx is the same. We got started late. Normally when someone asks that question, I'm like, oh, I don't know, are they? And then I just log off. And people are like, oh, how are you going to do us like that and not answer our question? You're like, Leach, it's literally your job to answer our questions. And I'm like, oh, I disagree. This is the fundamental disagreement between students and teachers. I could say it's not my job to answer your questions. It's my job to raise more questions. But the funnier way of doing that is to say, is it? And then just log off. That's a great thing about online school. I don't need to bring smoke bombs to class where I throw a smoke bomb down and then disappear. I can just log off, end the meeting. And it was like, oh man, how you do that to us? I just don't need the smoke bombs anymore. Because then the administration gets on my case. It's like, well, Leach, you can't be throwing smoke bombs in class. And I'm like, well, but how am I supposed to do my ninja disappearance? There's too many people in the room. I can't just do like Batman to Commissioner Gordon, where he turns away for some reason and then he turns back around and I'm not there anymore. I'd have to find some way to get all the students in the room to turn away so that I could sneak out. So I need the smoke bomb as a distraction. And they're like, oh, you could stick around and answer their questions because that's your job. And then I'm like, oh, is it? And then I throw a smoke bomb in the administrator's office and then I disappear. I'm just kidding. I've never thrown a smoke bomb in a classroom. I use the distraction technique. I just have to say, oh, look in that corner. The solutions to the final. Then if I want the class to think I'm an evil villain, when they turn around and I'm not there, I just play a recording of me laughing. So it's just like, ha, 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 and you just hear me laughing as I go down the hall. And then you, as the students, say, curses, he got away again. Yeah, that's the problem. Then I have to run back into the room and say, oh, don't forget to do your homework. And it just ruins the whole effect. You know what I mean? All right. So there was a lot going on today. I started, you thinking about chapter 15, because we need to have the basics of chapter 15. I didn't tell you how you're going to take those 4 second partials and combine them into one thing so we can determine whether we have a local minimum or a local maximum or neither. But it was pretty clear that that was the question that I was not going to be answering today. Also, second partial derivatives is from section 14.7. The finding critical points and classifying them, that was from chapter 15. Chapter 15 is about optimization. Second partials are in 14.7. You might be wondering what happened to 14.6, and 14.6 will show up. It's the chain rule. So that's where we're at. This is what we're going to be on about this week. That'll do it for today. I'll see you all tomorrow. Everybody have a good day, and thanks for playing.